In today's lesson, we're going to look at the normal distribution and z-scores again. We introduced that in the last unit. We're just going to work with some applications of it now to drive home some of the concepts. And hopefully by the time we finish this lesson, it will be obvious why it's a useful thing to use. So first, let's recap some of the things that we've done. First of all, some simple things. We know that mu stands for the population mean. If we're dealing with a sample, then we'd have x bar for the sample mean. We know that sigma, lowercase sigma, stands for the standard deviation of the population. If we are using a sample, then we use lowercase s to represent that. Same thing, different variables. We've also been dealing with a normal distribution up till now. It's the graph, so we've learned some things about the graph. We know that 68% of all data falls within one standard deviation of the mean. So again, the area under the curve corresponds to a percentage of the population. And so the area that I'm shading in yellow right now, it would be 68% of the area under the normal curve. And because it's symmetrical, we know that 34% of it will be to the right of mu, the average, and 34% of it will be to the left of the average. We know that 95% of data falls within two standard deviations. And that means that if I wanted to find out the area just under, say, this section here, which I've already filled in, but where did that 13.5 come from? Well, it comes from the fact that between these two lines is 95%. But we've already accounted for 68% of it here, right? So what's left over is going to be, well, 95%, just show the calculation, minus 68. That would be for both of these bars here, both the one I've already shaded in and this. So 95 minus 68 equals 27. But then we have to divide it in two because half of it goes here and half of it goes here. So overall, if we take that, we subtract and we divide by 2, that's where 13.5 comes from. And then the other 13.5 again is off to the left. And then we can, if we wish to, then we could figure out where the 2.35 come from. Well, it came from doing 99.7, which is what is the amount of data that should be within 3 standard deviations of the mean. And if we subtract 95 from 99.7, again, just to get the area of this, then we're going to get 2.35, which is at the end there. And then if 99.7% of the data is within 3 standard deviations, that means that 0.3% of the data to make up that 100% is outside, and again, half of that goes to each end. So 100 minus 99.7 divided by 2 gives me 0.15%. If we add all of these up, this plus this plus this plus this plus this plus this plus this, that would of course equal 100%. Okay, so that is understanding the normal distribution and the way that the probabilities play out. So we should also remember that the mean and the median are equal. We should also remember that we can, as we learned in the last lesson, we can use the normal distribution to model the frequency and population density distributions of continuous random variables. So all we've got now are, I think, 3 examples where we're going to put this to use to solve some problems. Right, the first one says, a police radar unit is set up to monitor vehicles on a stretch of highway with a speed limit of 100 kilometers per hour. Long-term records show for this location show that speeds vary normally. So when they say very normally, that's not just talking like, oh, they're normally this. This is being used in a scientific way. So saying something varies normally in this case means if we were to look at a graph of all the data, it would look like this. All right, so that's what they mean by varies normally. With a mean of 105 kilometers per hour, all right, so that's actually more useful than this one. Unhighlight the 100 and actually highlight 105 because that is our mean, and the standard deviation is given as well as 7 kilometers per hour. Drivers who exceed the speed limit by 20 kilometers per hour accumulate demerit points as well as pay fine. Okay. So long-term records. So again, this often some interpretation required in data management, a bit more so than in other math courses. Long-term records is meant to sort of signify, to indicate to you that we should treat this as a population. Long-term records, in other words, they've got all the data. They've got so much data, in fact, they're going to consider it to be the whole population. What percent of drivers will accumulate demerit points? All right, so the speed limit's 100, but if you go 20 kilometers over, you're going to get demerit points. So to get demerit points, that means that X is going to equal 120. In other words, they want to find out what percent of population is going to be actually not equal to 120, but greater than a speed of 120. 120 or more will get you demerit points. So we can calculate the z-score for if X equals 120, and that would be 120 minus the mean, which was this, 105, divided by the standard deviation, which was 7, and I get a z-score of 2.14. This is what we look up, right? This is what we use the tables for. But I'll come back to actually looking it up in a second. Because to get the probability, well, actually, before I actually do a calculation, here's what you should always do for these ones. You should always draw yourself a little picture just so you can see what's going on. So use my line drawing tool to get a nice flat base here. And I'll draw my normal sketch of my normal curve over it. And just put some critical information on here. The mean is in the middle. That's mu. That's 105 kilometers per hour. We want to find out what percent of drivers are going to be caught driving 120 kilometers an hour or more. So this is the crucial part. We want this section of the graph. Okay? The reason why that's crucial is because, as we saw before, z-score tables only deal with the other portion of the graph. They only deal with this portion of the graph, and so we're going to have to do a little extra calculation to get what I've shaded in blue. But that's not a big deal. That's easy, in fact. So we want to find the probability that X is greater than 120. If we want to find that it's greater than, if we want the blue part, then we're going to do 1, or for 100%, minus what we look up on the z-score table. So, which is the equivalent of finding 1 minus the probability that X is less than or equal to 120. That's what the z-score table tells us. So now I'm going to go back to this, That's what I'm looking up on the z-score table. Z-score table. And remember, it starts at the smallest percentages. It starts with a z-score of negative 3.49. So it's starting down in this corner. So basically 3.5 standard deviations below the mean has a probability of occurring of 0.0002 or 0.02%. And then as we go this way, because we're dealing with negative numbers, as we go this way, we're actually increasing, right? Because negative 3.48 is actually greater than negative 3.49, and so on. So as we're going up, then we'll notice that the probabilities are also going up. That only applies for the negative side. We're dealing with a positive z-score. Remember, it was 2.14, I think, and where is this from the previous one? So I find 2.1 on the z-score table. That's this row here, and then I find the 4 for that second number. 4 was up here. I find the intersection of these two things, and I get 0.9838. So that's the probability that a given motorist would be driving 120 or less. It's also the percentage of motorists that are driving 120 or less. So 98.38% of motorists drive 120 or less, according to this data. Since we want the percentage that's going over that, though, we subtract it from 1. We find the difference between the two, which works out to be 0.0162, or 1.62% of drivers. And since this question asked for it as a percent, I'll give it, actually write that down, just drivers. That's how we can use the z-score table for an application. What's the probability that a given vehicle has a speed between 99 and 101 kilometers per hour? So again, now we're not looking for percentage of drivers. We're they're going to accumulate the merit points or whatever we're using for probability. But again, they're very closely related to each other. Let's start with the sketch again. Sketch, so important. That wasn't bad until the end. Commenting on my sketch drawing skills. But anyway, that'll have to do. All right, so again, we got the same mean of 105. We want to find the percentage that falls between 99 and 101. All right, so that's down here. Let's exaggerate the difference between them a bit. But let's say 99 is here. And let's say that this is 101 over here a little bit so I can separate them a bit. It's a pretty thin stripe of colored area here, right? Just between those two numbers. Remember, we saw last lesson that if I want to find a bar that's in the middle like this, I have to do two separate calculations and subtract the smaller one from the bigger one. Really what I would do is I would find the whole area that's less than 101, and then I would subtract the area that was less than 99, and what I would be left with is the blue area, right? So I need to calculate both of those and then do my subtraction. So that's exactly what we're going to do. So we have to do two different things. So we're trying to find the probability that x is greater than 99, less than 101. I'm not going to worry about or equal, or I'm not going to worry about these signs underneath right now because we're dealing with probability and it's a small difference between the two different things, so I'll stick to just greater than or less than signs without the or equal to. Don't get confused by that. So as I just explained, this probability is going to be the same as the probability that it's less than 101. Again, x is less than 101 minus the probability that x is less than 99. Again, that's what I just showed on the graph. That's why graphs are helpful so you can see what's going on. The only way I'm going to get those two probabilities is from my z-score table, right? So maybe as an aside over here, I'll calculate the z-scores. So the z-score when speed is 101, that's my x value, so 101 minus 105, the mean standard deviation is still 7. That gives me negative 4 over 7, or negative 0.57 to 2 decimal places, which is again what I need. This is what I need to look at. So if I look at negative 0.57, 0.57 on my z-score table, let's go to the negative side. So negative 0.5 to start with. Okay, and I want to go over to where 7 is. The 7 is here, so I'm going to go down this drawing on this to make it easier to zero in on the one I want. There we have it as 0.2843. Okay, so let's write that down before we forget. 0.2843. So that's what this is. And then I'm going to do it again for an x value of 99. That equals negative 6 over 7, which is approximately equal to negative 0.86. That's the next one we have to look at. Let's get rid of this so that we have a clean thing to look at. Negative 0.8 is here, and then 6 is here. So we are looking at 0.1949 as the intersection of those two. And that's the one that I'm going to put in for this. Okay, the difference between these two is 0.0894. So the probability that a given vehicle is going between 99 and 101 kilometers per hour would be 0.0894 or 8.94%. So approximately 9% probability. 9% of the vehicles will be going between those speeds, and that would correspond to our probability. Example 2. Suppose the birth mass of a breed of guinea pigs follows a normal distribution with a mean of 100 and a standard deviation of 10 grams. What's the probability that a birth mass from a large sample lies within a standard deviation of the mean? Well, it doesn't matter that we're dealing with guinea pigs. It doesn't matter that the average mass is 100 or the standard deviation is 10. As long as there is an average and there is a standard deviation, we know that always 68% fall within standard deviations, fall within one standard deviation. And we say SD for standard deviation. We know from above, from up here, that 95% fall within two standard deviations, right? Here's one standard deviation, 68%, 95% for two standard deviations. So this question doesn't really require a lot of work. You just have to remember the fact. 2 standard deviations. So how do we incorporate the 100 and the 10? Well, again, as far as answering this question goes, they don't matter at all, and it doesn't matter that they're guinea pigs. In this case, 100 would go here for the mean. Mu plus 1, this one here, just means 100 plus 10. So 110. Mu minus 1 standard deviation would be 100 minus 10. So in other words, 68% of the guinea pigs would be between 90 and 110 grams. And then if I want to add 2 standard deviations, well, it gets to 120 for adding and subtracting. There should be a minus sign here. Nope. Try again. What have I done? Mu minus 2 standard deviations. There we go. So 100 minus 20 is 80. And so 95% of the guinea pigs are going to be between 80 grams and 120 grams. So the answer part B, does the answer part A depend on the mean and the standard deviation? Absolutely not. The whole point of having a standard normal, well, not standard, just a normal distribution means that as long as we know the mean and the standard deviation, we can plug in different numbers and it's going to follow the same pattern. It's all about the pattern, okay? So that is an important concept. The probabilities are the same for all normal distributions. All right, last example. An electric car requires a mean recharge time of 4.5 hours. All right. Well, if that's our mean, then that's our mu. If the batteries are fully depleted, the manufacturer guarantees that the car will fully recharge in no more than 5 hours. That looks like it's probably going to be an X value somehow, right? If the probability that a recharge takes more than 5 hours is to be kept to 1%, what's the standard deviation of the battery recharge time? So to wrap our heads around what this question is asking is, put yourself in the place of the manufacturer. They know that it takes 4.5 hours on average to recharge their batteries. They want to guarantee, they are guaranteeing that it won't take more than 5 hours. But they know that there's still going to be some variations. Sometimes it will take more than 5 hours, and they expect that's going to happen, and they expect that some people are going to return their car or their battery and call it defective. So they're expecting that to happen, but they want to keep the percentage of those claims small. They want to keep that to 1%, right? So they want only a 1% return rate. So the only thing they can really play with, since they've already set the mean and the probability of this happening at 1%, and then this is really, like I said, going to correspond to our X value, is they can only play with the standard deviation. Well, what formula do we have that connects these things together? Well, it's the Z-score formula. The Z-score is equal to X, which is 5, minus mu, not mu, yes, sorry, over mu, minus mu. Good thing this is the last example, getting tongue-tied. X minus mu, and we're going to divide it by the standard deviation. Well, we know what x is, we know what mu is, so we know what, we want to find what standard deviation is, sigma. Do we know what z is? No, we don't know what z is, but we can find z from this. Let's look at a sketch and think about it. That's almost my best one yet. Mu, 4.5 hours. X, 5. We want 1%. We want to have 1% or less greater than 5 hours. So let's make that, it's going to need to be really close up to the end here, isn't it? So 5 would have to be here in order for this to be 1%. We want that to be 1%. All right. Well, in that case, that means, again, using z-scores, that means that we want this whole part here, the part that we can actually measure using the table, to be the rest of it. This part has to be 99%, doesn't it? Again, in case you're lost, the reason why I'm looking at this bigger area is because we're always measuring to the left of our line. Our z-score tables are always looking at things that are to the left of the line, right? So that is the whole reason why, even though it talks about 1%, because it's the upper 1%, I need to use the rest of it in 99%. All right, so now we know it's 99% of the time. We could reword this to say that the battery needs to recharge in 5 or less hours 99% of the time. So, what's our z-score going to be based on? Based on this. So I'll go to my z-score table, and I need to find 99% on this table. Well, we know that this side of the table with all the negative z-scores, the highest percent we can find is here at 0.00. In other words, right at the mean, 0.00 standard deviations below the mean is the highest this side of the table goes. That makes sense, should make sense anyway, because at the mean, you've exactly cut the normal curve in half, so 50% is to the left and 50% is to the right. We need to go over to the other side and go all the way up to 99%. But let's not overshoot this here, because this table goes up to 99.98%. That's as high as we can go. So we want to find the one that not just 99.98, we want 0.9900 is what we're looking for. Well, where are we going to find that? And we don't find that exactly, but we find it approximately. The closest I can find is right here, 0.9910. So working backwards, that means that I've got we're in the row that has 2.3 and the column that has 0.03. So when I put that together, I get 2.33. Let's push the wrong button. Go back to class notes now. Sorry, things are laggy now. Here we go. All right. So that means our z-score is 2.33. So we've got x, we've got z, we've got mu. Let's put them in. 2.33 equals 5 minus 4.5 over sigma. And let's rearrange this and solve it for sigma. So if I multiply both sides by sigma, it comes over to this side, divide both sides by 2.33, and as I subtract at the same time, I get 0.5 divided by 2.33. That's just rearranging it. And 0.55 divided by 2.33 equals 0.215. What does that mean? What are the units? Well, the standard deviation units are always the same as the units that we're measuring, mu and xn. So we're talking hours. So the standard deviation has to be 0.215 hours. If you want to be a little bit more, when I think about that in terms of minutes, I'll go 0.215 times 60, so, or approximately equal to 13 minutes. Not that I need to use minutes, in fact, I should stick to hours, strictly speaking, for doing my calculations, but just to wrap it up and wrap your head around it, the standard deviation has to be only 13 minutes.